Hello guys, welcome to my YouTube channel. In today's video, we're going to discuss about ordinary differential equations. In that, we're going to discuss about the exactness, the integrating factors, along with that linear ordinary differential equations. So before we start the video, please press the like button, share it along with your friends, and do subscribe so that you'll be getting immediate notification as soon as I post the video. Please kindly share the video because it will be really encouraging and motivating me to do more and more of these. So let's get starting. Let's start with exact first order differential equation. In this, let us consider a first order differential equation of the form mxy dx plus nxy dy is equal to 0. This is said to be exact if and only if dou m by dou y is equal to dou n by dou x. In this, one thing we have to remember is that here m is associated with dx and n is associated with dy. Therefore, we have to differentiate it with the opposite sign, that's dou m by dou y. Here you can see dx, so we have to differentiate it with the opposite one. Similarly for n, it's associated with dy. We have to differentiate it with dx. So if this condition is satisfied, the equation is said to be exact. So let's now look with an example. Here, let's consider an example 3x square plus 2 e power y dx plus 2x e power y plus 3y square dy is equal to 0. Now in this case, it's of form mxy dx plus nxy dy is equal to 0. Here we can take that mxy is equal to 3x square plus 2 e power y, and here nxy is equal to 2x e power y plus 3y square. Now if we partially differentiate it with respect to y, considering that x as a constant, we will be getting 2 e power y. Similarly, if we partially differentiate n with respect to x, considering that y as a constant, we will be getting 2 e power y, and this term will become 0. Since dou m by dou y is equal to dou n by dou x is equal to 2 e power y, the equation can be said to be as exact. Therefore, now let's start solving it. Since it's exact, there exists a function f of xy such that dou f by dou x is equal to m, which is this function, is equal to 3x square plus 2 e power y. Let's consider this as equation 1. And for the second part, let dou f by dou y is equal to n, which is equal to 2x e power y plus 3y square. Let's take this as equation 2. Now after this, let f of xy is equal to integral 3x square plus 2 e power y dx plus g of y. Now here I am taking dx plus g power y because I am considering only equation 1, and in equation 1 we'll just be integrating with respect to x over here. So we wouldn't be having any y term. That's why I'm adding plus g of y to it, so that we'll be getting the equation in terms of x as well as y. So after integrating this, we will be getting x cube plus 2x e power y plus g of y. G of y is the function of y obtained such that g of y is such that it f of xy satisfies equation 2. That's this equation. So now d of dou f by dou y is equal to n, which is equal to 2x e power y plus 3y square. Now this equation must be equal to 2x e power y plus dg by dy. Here, after observing this, we can understand that dg by dy is equal to 3y square. Here I am mentioning it as dg by dy but not g, because here we are having as an integral differential form, not and here it's present in an integral form, which is as a normal equation, but here it's present in a differential equation. That's why I'm mentioning it as dg by dy. After this, we can observe that dg by dy is equal to 3y square. Now if we integrate it, we'll be getting as gy as y cube. Hence f of xy is nothing but x cube plus 2x e power y plus g of y is nothing but y cube. Hence I can write this equation over here. Now the solution of given exact differential equation is x cube plus 2x e power y plus y cube is equal to c. Now let's take a look at integration factors. Till now we didn't have any problem, whereas now we have a big problem. What if the equation is not exact? What if dou m by dou y is not equal to dou n by dou x? It's a very simple rule that if we are not having exactness for the differential equation, we will be multiplying it with an integrating factor. Here, if the first order equation is not exact, then sometimes it can be multiplied with an integration factor. I'll be using IF everywhere in this video, which represents integrating factor. So we have three theorems to look at for integration factor. Theorem 1. If dou m by dou y minus dou n by dou x whole divided by n represents us a function with only and only x present in it, then the integration factor is given by e power integral f of x dx. This term must be multiplied with the given differential equation. This is the theorem 1. Now let's have a look at theorem 2. If dou m by dou y minus dou n by dou x divided by m is equal to minus gy, we have to have a careful look over here that it's minus g of y, it's not g of y. Let's suppose we will be getting this equation as 1 by y, then we must consider minus g of y is equal to 1 by y. Hence g of y from that will be taken as minus 1 by y. I hope you will be understanding it. Then the integration factor is given by e power integral gy into dy. In this thing you need to be smart enough in understanding that you must get an equation of f of x or g of y, and it must not involve both x and y. It must contain either x or y, and hence you must be smart in deciding whether you need to divide the equation with respect to n or m. Now let's go to theorem 3. If mx plus ny is not equal to 0, then the integration factor is equal to 1 by mx plus ny. Else, if this one mx plus ny is equal to 0, then the integration factor is either 1 by xy or 1 by x square or 1 by y square. Now we have understood the three theorems for integrating factors. Now let's go further by solving a problem. Let's take this problem as 5x cube plus 12x square plus 6y square dx plus 6xy dy is equal to 0. Now this is of the form again mxy dx plus nxy dy is equal to 0, wherein the m is 5x cube plus 12x square plus 6y square and n is 6xy. Here if we have a look at it, dou m by dou y gives this term because x is assumed to be as a constant, and after differentiating it, it becomes 0. Here 6y square becomes 12y after differentiation, and here dou n by dou x is equal to 6y. Here we can carefully observe that dou m by dou y is not equal to dou n by dou x, hence the equation is not exact. Now let's have a look. If we divide it by m, if we divide dou m by dou y minus dou n by dou x by n, then we wouldn't be resulting with anything because it's a very big equation, and you wouldn't be getting either in terms of x nor in terms of y. Now the similar equation dou m by dou y minus dou n by dou x, if we divide it by n, then it's 12y minus 6y by 6xy. If we do this, we'll be getting it as 1 by x, and it's in the form of f of x. Since it's satisfying the first theorem of staying as f of x, we can take the integration factor as e power integral f of x, which is equal to e power integral of 1 by x. Now integral of 1 by x is ln x. I've put a mod because we don't know x is positive or negative. Now e power ln x is nothing but again x. This we'll be understanding. Alright, we got our integration factor as x. Now multiplying the equation with integration factor x, we will be getting it as 5x cubed plus 12x square plus 6y square into x dx plus 6xy into x dy is equal to 0. Now, after the multiplication, we get it as 5x power 4 plus 12x cubed plus 6xy square dx plus 6x square y dy is equal to 0. Now after shuffling of the terms, we will be getting it as 5x power 4 plus 12x cube dx plus 6x square xy square dx plus x square y dy is equal to 0. Now after the integration, we will be getting it as x power 5 plus 3x power 4 plus 3x square y square is equal to c, wherein c is the constant of integration. This is the final answer of the problem. Now let's have a look at another problem over here. 2xy plus x square into y dash is equal to 3y square plus 2xy. If we have a look at it, it's present as y dash. Now we can write y dash as dy by dx. Here 2xy plus x square into dy by dx is equal to 3y square plus 2xy. Now I'll send this dx over here and bring it back to form a single equation. It becomes 3y square plus 2xy into dx minus 2xy plus x square into dy is equal to 0. Let this be the first equation. Now here we can observe it as mxy dx plus nxy dy is equal to 0. From the theorem 3, we can observe that mx plus ny is equal to 0. Then we can write the integration factor as 1 by mx plus ny. Here mx plus ny is 3y square plus 2xy into x minus 2xy plus x square into y. After solving this, it becomes 1 by xy square plus x square y, which is equal to 1 by xy into x plus y. Now multiplying the equation 1 with the integration factor, that's 1 by xy into x plus y. Here I have took y common from here, so that becomes y into 3y plus 2x by xy into x plus y. In this n, I had took x common, hence that becomes x into 2y plus x by xy into x plus y dy is equal to 0. Now let this be equation number 2. Hence the equation becomes exact since we had multiplied it with the integration factor. After becoming exact, I've already mentioned you how to solve the problem. Now since it is exact, we can consider a function f of xy which satisfies this equation such that dou f by dou x is equal to 3y plus 2x by x into x plus y. Now after splitting this and taking partial fractions, we will be getting it as 3 by x minus 1 by x plus y. Let this be equation 3. And in the similar manner, we will be getting dou f by dou y as minus 2y plus x by y into x plus y. After splitting it and taking partial fractions, we will be getting it as minus of 1 by y plus 1 by x plus y. Now let's look at the equation. F of xy is equal to 3 by x minus 1 by x plus y dx plus g of y. This we will be getting it with df by dx, and this g of y term is present because we hadn't done any differentiation with respect to g of y. Now here after integrating this, we'll be getting it as 3 ln x minus ln of x plus y plus g of y. Let this be equation 5. Now since this f of xy satisfies both dou f by dou x and dou f by dou y, we can substitute this in dou f by dou y too. But remember that we have to substitute g dash of y, because we are taking dou f by dou I, that is in the differential form, and here it's present as an equation form. That's why we'll be taking dou f by dou y as minus of 1 by x plus y plus g dash y. Here it this equation is nothing but dou f by dou y, which is equal to minus 1 by y minus 1 by x plus y. Now if both the x plus y remain the same, and hence g dash y is nothing but 1 by minus 1 by y. Now after integrating this, we'll be getting g of y as minus ln mod y. Because we don't know y is positive or negative, we'll be taking it as mod y. Now hence the equation f of xy becomes 3 ln x minus ln x plus y minus ln mod y. This is equal to ln c because c is the integration constant. Now if we remove ln from every side, we'll be getting it as x cube by y into x plus y, since log a minus log b is log a by b. Or this equation can be written as x cube is equal to c into y times of x plus y, wherein c is the integration constant. So this concludes our integration factors, and now let's have a look at linear first order differential equation. For a linear first order differential equation, it must possess a form such that f of x dy by dx plus g of x y is equal to h of x. It's very similar to a quadratic equation form, but only thing is we must have a differential form over here with y form in the other thing. What's the difference between a quadratic and linear first order differential equation is that here there will be no quadratic term, and the only term will be dy by dx, or this can be rewritten as dy by dx plus p of x y is equal to r of x, wherein p of x is nothing but g of x by f of x, and r of x is nothing but h of x by x by f of x. So we have a theorem for solving linear differential equations. So if the integration factor of non-homogeneous first order linear equation y dash plus px of y is equal to rx is given by e power integral of p of x dx, this p of x term into dx. Now let's look at it with an example. Here is the example. X into dy by dx is equal to 2y plus x power 4 plus 6x square plus 2x, wherein x is not equal to 0. Now this can be solved by dividing the entire equation with x. We'll be getting it as dy by dx minus 2 by xy is equal to x cube plus 6x plus 2. Now the integration factor is nothing but e to the power of integral px dx. So here p is nothing but minus 2 by x. Now we are taking the integration factor as e power minus integral 2 by x dx, which is equal to e power minus 2 ln x. This ln x we'll be getting after the integration. Now ln x is nothing but 1 by x square, because the minus 2 is present over here. Hence the integration factor becomes e power of 1 by x square. Now after multiplying the equation 1 by the integration factor, this becomes 1 by x square dy by dx minus 2 by x cube y is equal to x plus 6 by x plus 2 by x square. Now this is nothing but dou by dou x into 1 by x square into y is equal to x plus 6 by x plus 2 by x square. Now y by x square is nothing but x by, this is done by sending dx to the other side. If we send dx to the other side and integrate it, we'll be getting this one. Now x becomes x square by 2, 6 by x becomes 6 ln x, plus 2 by x square becomes minus 2 by x, plus c, which is the integration factor. Hence the overall equation can be written in this form as y is equal to x power 4 by 2 plus 6x square ln mod x minus 2x plus cx square. This concludes today's video, and with the next video we'll be discussing about some special first order differential equations which involves Bernoulli's, Riccati's and Clairaut's equation. Also, we will be discussing about orthogonal trajectories in the ordinary differential equations. As I at first mentioned, please like the video, share it with your friends and subscribe so that you will be getting my notifications immediately and you can watch my videos. Thank you so much.